Good evening, ladies and gentlemen. My name is Claudia Eberlein. I'm the Dean of the School of Science, for those of you who are not from Loughborough. And it's an absolute pleasure for me to introduce to you our speaker of today's Mott lecture, Professor Laura Greene. Now, I've known Laura for a very long time. I first met her in 1993 when I came as a postdoc. It was my first postdoc position to Urbana-Champaign, Illinois, and actually the year before Laura had just started there. And she'll say something about the various things she did in her career, and she'll talk a bit about the science she's done and a bit about her life as a scientist. So currently, she's the Marie Krafft Professor of Physics at Florida State University, at the same time the chief scientist at the U.S. National Magnetic Field Laboratory in Florida. She's also a member of the U.S. National Academy of Sciences and the American Academy of Arts and Sciences. She was previously, in 2017, the president of the American Physical Society, and in September 2021, she was appointed to the President's Council of Advisors on Science and Technology. And I think she'll show us in a little while a picture of her with the President of the United States. So when she showed that to me, I sincerely apologize that it's not within my gift to get her into an audience with the Prime Minister in the UK. She's won numerous medals and awards, so if you look on Wikipedia under Laura Greene physicist, then there's quite a lot to see. In addition to being a physicist, she's also been a firm voice for diversity, especially for women in physics or more generally in science and technology. And it's telling that we essentially met, she and her, by me having the same sort of issues with the same person in the department at the time. She's generally been a great supporter for women in STEM disciplines. She's also the mum of two beautiful boys, Max and Leo. And I remember learning really essential things from Laura, like parenting skills when little, I think it must have been Leo at the time, didn't want to go to bed. Mum asked, "Do you want to walk upstairs or do you want to be carried upstairs?" And the little boy was so busy thinking about the alternative that he didn't question that he had to go to bed. So I memorized that, and it helped my parenting skills when I was at that time. She also plays guitar, so when you look her up on the White House website, then you see a lovely picture of her and her acoustic guitar. Her work has been primarily on such important subjects as high-temperature superconductivity, and she'll explain about that, but also on diversity in STEM. There isn't so much more I can say that she couldn't be putting very much better. So, ladies and gentlemen, let's welcome Professor Laura Greene.
Thank you, Claudia. Am I on? No, I'm not on. Yes? Are you hearing me? Yes, okay. I'll drop this in my pocket. That'll be 25 cents. Okay. So I'm hoping this is a fun talk. I will show you an outline, but that's my plan. But Claudia asked me to say something about myself, and I do have a lot of accolades. It's been great. But I'm not going to just come up here and say, "Oh, I was so lucky, everything was great." It was a battle. And it's a battle for everybody to be successful in physics or anything at all. And so I like to tell just a couple of the stories. Here's a sentence that I used a lot. Being a physicist is not simply my job or my career, but it's an integral part of what defines me. People my age, I can tell you right now, I'm 70, okay? Women my age that are in physics were not encouraged. Were only discouraged. And it was like a calling. It really was like I had no choice. Even though I was told I'm not going to find a husband, I'm not going to find a job, I just felt I had to do it, and every day I had in physics was, to me, special. But it's always been a battle. And I remember, when I went through all the science books in elementary school, I asked for more, and they gave me, kids' books. And I liked them, but I would go out to the library and find all these things. When I got a bachelor's degree at Ohio State University in 1974, and there were only 2 women in the entire undergraduate group. And of course, there were no people of color. I mean, that's still, it's all a major problem right now. And I was afraid to go to graduate school because I was scared. So I took a job in aerospace to get out of debt and to also just take a break. And there I learned that I was hired because I was a woman. And the fact that I think I told you this already, because I got something done, one of the other aerospace companies came by and said they'd offer me twice the salary. And then you could get away, anybody could get away with anything. If I ever went to someone and said, would you do this for me? They would, if you asked for anything, the statements you would hear would be, that's frustrated B, what she needs is a good L. You can fill in things. And what I found, what was helpful for me, was to, say that may be the case and make a joke out of it. I would like to make it so no one has to do that anymore, but that's how it was. So anyhow, then I went back to graduate school, and I got my PhD in graduate school. And one interesting thing is there were over 250 graduate students, and there were only 4 women. And so we got together for lunch every week or 2. And what happened is this grew into whole women in science lunch. And in 2017, I was invited back, and there was a whole conference. That Women in Physics group had been going on for 40 years. And I don't know why it was so special, but it certainly worked out. Anyhow, I got to graduate school. I was in the Bell system for 9 years, which was fantastic. I was there during the high TC days. You learn to get tough, and I'll tell you a little bit about high temperature superconductivity. And then I got my job at University of Illinois. What I didn't tell you, what I also did between my bachelor's and graduate school, is I worked a little bit in parapsychology. Yes, I did. Yes, I don't believe any of it, but I was so curious, I went and did it anyhow. And those are also great stories. I had a lot of hits at Bell Labs. I had a lot of hits at University of Illinois. There were a lot of struggles. For instance, there was no one ever heard of childcare. It was all sort of interesting. So people say, did you plan your career to be like this? And my answer is no. What I already told you, every day I was trying to be in physics. I thought I'd really be lucky if I got my degree, I got a job somewhere, maybe I'd have a little lab to work in once in a while, and maybe every few years go to a conference. So I never expected any of this, and I didn't plan it, right? I just was, I also put myself in the right place. I also worked like a dog. I didn't complain, and what I'd like to see is that minorities and women don't have to do what we do, right? We all, like Claudia and I, yeah. At my age, I don't hashtag Me Too, but we got our old girls network, and it's been tough. And what I would tell any minority, and you guys, white guys too, you're going to run into times where you think you're going crazy, it's difficult, how do I deal with this, why is this happening to me? And what you need to do is contact your friends. We used to call, nobody calls anymore, sometimes you call, and what you do is you listen to your girlfriend or your other friend, and you let them talk, you say, oh, poor, poor, and you electronically turn around and push them back out in the world again. And you can do that for each other. It's part of networking. But yeah, there's been some challenges. I didn't really get involved in women's issues until I got to the University of Illinois, because I went from Bell Labs to University of Illinois, because there weren't any. And then all of a sudden, I'm at the university, and that's when I started to get much more involved in diversity. I've been working in human rights for decades, but this is really, diversity is also falls under the umbrella of human rights. And what else helped me? I guess I don't really need to say much more, but besides all this human rights, the other thing that I've been lecturing on a lot and doing a lot is something called science diplomacy. And if anybody wants to talk with me about that later, I'd be happy to. But what that is using the language and the acts of science to basically communicate across borders and boundaries and build a better world. It's not what it was in the 50s. I can give a whole lecture on that. Now what's going on in Ukraine, what's going on in other countries, it's become a very complex issue. So if anybody's interested, I'd be happy to talk to you about it sometime. So what else do I have to say? Well, here's the picture I promised. So there we go. That's me and Joe. So that's me. My kids pointed out to me that I was the only person smiling in the picture. And it's low resolution because I didn't get this picture. I wrote my boss at the magnet lab, that I'm sorry I had to be away for 2 days. I had to fly to Washington. And he actually saw this, and it was on the local TV station. He took a picture of it for me. So I wish I had more pictures. He's pretty cool, by the way. I just thought I'd say that. So let's go on to the talk. I'm hoping this will be fun. I don't know if you're going to learn any physics at all. You're going to learn a little about the magnet lab. Why the title? It's basically to get people interested in superconductors and what we call unsolved quantum matter. I've got a fun analogy. I'll show it to you. But my analogy goes over, I'll be talking about gravity waves, and I'll just touch a little bit on the quantum matter. You're not going to learn much on this, so I just want to flash it to you. But when the gravity waves were discovered by LIGO, the black holes, the colliding black holes, which were measured by LIGO, and I'll mention that again, they go across the entire universe, and that much energy, 10 to the 49 watts. What I'm talking about here, and since I won't have time to really talk about it, that picture is something called electron nematicity. And before certain high temperatures go superconducting, the electrons clump up at a high temperature, and we don't know why. So one thing that I'll just gloss over is that before it goes superconducting, the high temperature superconductors, and what I'll tell you about the unconventional superconductors, do very strange things. They get into waves, they line up. These are completely unsolved problems in physics. Just like we don't understand dark energy and dark matter, we don't understand these things. So these problems are no less fundamental, yet they range 10 to the 36 in length and 10 to the 70 difference in power, which doesn't mean anything, but it's a nice number. So outline is, what is a superconductor? I'll go over some of that. What is the National Magnet Lab? Most of my talk will be on advertise the Magnet Lab because most people know what's going on there, and it's so cool. I'm sorry, that's a joke because superconductors have to be cooled. Okay, and then I'm going to mention what is an unconventional superconductor, which is different. I'll bring it in a few times. And then my cute little analogy. So I found this. I can go onto the web and find things and copy them and put them on my slides too. But I have this one, caution analogies ahead. So if any of you are physics or have gone through some basic physics courses, what this is a picture of on the right is the Bohr model of the atom. We love that analogy. It works. It helps us understand quantum mechanics. And when you push it too far, it's completely wrong. So let's keep that in mind when we talk about analogies. So if you've ever been to a high energy physics talk, you always have a picture of the collider, which doesn't mean anything. I'm a low temperature physicist. I have to have a picture of the discovery of superconductivity. So this was discovered a long time ago. Okay, it was discovered in 1911. They were just trying to liquefy helium, and they decided to measure a metal. And no one ever thought that as the temperature was lowered, you take a metal, and the temperature is lowered, and typically the resistance lowers, and I'll mention that in a second. All of a sudden, the resistance dropped completely to zero. Okay, I'll tell you what that means. No one predicted that. Some people thought if you lower the temperature, the resistance would go up or would stay the same. Nobody predicted this. And almost all of superconductivity, almost everything, is 100% serendipitous discovery. Just to show you what happens, I want to show you this little picture because I'm going to use it right at the end. So what happens, in fact, I'm going to go ahead and then I'll go back. I think I'll skip that one. So this here is the discovery of superconductivity. I'm very bad at this point, right, in 1911. And this is the discovery. These are all other superconductors that have been discovered. I have left off most of the families of superconductors. What's in red there are the superconductors which are called conventional superconductors, and we understand them. The ones that are all the other colors are unconventional superconductors, and we don't know how any of them work. Okay? So I'm going to do this on here because I'm having trouble with my pointer, even though it's a great pointer. So I mentioned to you that when something superconducts, the resistance falls to zero. Zero resistance is one of the properties. So on the upper left, we have a normal metal. As you lower the temperature, the resistance goes down because the electrons are moving in a, when you're boiling water, the lattice is moving, it's boiling. Same thing true with metals, that everything's moving around at high temperature, and you cool it down, it slows down. And typically, the resistance falls. Sort of what happened to that blue curve for a normal metal. In a superconductor, below a certain temperature, a low temperature, the resistance falls to 0. The other property of a superconductor is that it spits out all magnetic fields. It's diamagnetic. It just will not let a magnetic field in there. Now, I just want to show you, before I do that, I wanted to go back to this one. So what happens, the way conventional superconductors work is that the electrons all work together in a group. And how do they do that? It turns out this is one of the few quantum materials problems that have been solved, one of maybe 2 or 3. And what happens is an electron goes through a lattice like niobium, or if you've been in an MRI, niobium titanium. And what it does is that below a certain temperature, the electron has a really strong interaction with the lattice and it pulls it in. So it leaves, like a boat, a positive wake. And the other electron sees that. And this is actually, it's not just pairing, it's a many-body effect. And so the electrons distort the lattice and cause other electrons to go over there. Because the lattice, the ions are positive, the electrons are negative, and they get pulled together. That's the basis, that's the cartoon analogy of this theory called BCS superconductivity that was actually discovered where Claudia and I met. So I already went over this one, and I went over this one. What does zero electrical resistance mean? It would be great for energy. That could be an application. So this is a space heater. And if you have a space heater and you plug it into the wall and everything's working right, the copper wire stays cool and the coils inside get hot. Why? If you unplug it and look at the coils, there are these hard, crunchy-looking pieces of metal. And it's specifically designed to make it difficult for the electrons to go through. And it's kind of like friction, the resistance, right? Okay, it's hard to get your hands warm if you have oil on your hands and you're doing this, right? Because the resistance is lowered. So what happens is that a copper wire has low electrical resistance, and the heater wire has high electrical resistance. The copper wire, since it has low electrical resistance, doesn't dissipate that heat. The heater wire dissipates heat. What happens in a superconductor is the resistance isn't low, it's actually 0, no loss. So if I had a light bulb here and a light bulb in Scotland, and they were connected by superconducting wires, there would be no loss to the light bulb with light. So there are applications to energy. So that's what zero resistance means. The next thing is that what does, I thought I fixed that one. What does diamagnetism mean? Diamagnetism, or this ejecting of the magnetic field, is another property of a superconductor. And I put this in here because I've got a cute little video that I'll show you. What happens, remember, the electrons move around without any loss all around the material. You put it onto a magnetic field, and the electron says, we don't want you. And they set up a current, and they set up a current, I'll show you an example, and they spit out the magnetic field. And I'll show you what that means. That leads to magnetic levitation. So here we have something on the left, which maybe you've seen this before. That's this high temperature superconductor below being cooled, and that's a little magnet on the top, right? And one thing I like to point out is it looks very stable. That's strange. It turns out there's something called Harshaw's theorem, and you can't balance magnets on top of each other. They'll just fall over, right? You have to hold them together somehow. So there's these things, and I'll tell you in a second, actually it's very stable. So there are applications. So here's an example of a maglev train in Japan. They've actually this is a superconducting maglev train. If you've been on the one in Shanghai, that's not superconducting. There's designs that you can make it work. But this is one that there is a prototype out of high temperature superconductors. They've actually had superconductivity, I said, has been around since the 1900s, over 100 years. And the conventional superconductors were used, and they actually have a prototype superconducting levitated train that goes about 1 kilometer. And my friends in Japan always say it just travels far enough to take their funding agents for a ride. So that's pretty good. So the reason I wanted to show you this picture with how stable it was is because I want to point out that, remember I told you that ejected magnetic field, okay? Well, it turns out that all practical superconductors allow some magnetic field to enter. Okay, I'm going through this because the video is so cool. So bear with me if it's technical for a second. But so if this is a superconductor here, it allows some magnetic field to go through, and then the electrons around it, the superelectrons, keep the rest of it superconducting. So if we look at this picture here, the parts in blue are superconducting, and the parts that the lines are going through is magnetic field, and they're not superconducting. And a big key to applications is making sure that those vortices where the electrons are going around the magnetic field don't move. Why? Because here, these central parts that are not superconducting, if they move, they're not superconducting, they'll dissipate energy. So for applications, these kind of materials will take higher fields, but you have to find a way to pin the vortex. Okay, so that's the whole background of superconductors. Now I'm going to go on to the magnet lab, and I won't get through all the, because I'm adding too much stuff here. But I just want to tell you a little bit about the magnet lab, give you some science examples. So the magnet lab, which started out in Boston, now since 1990 has been in Florida, northern Florida. There's actually 3 sites I'll tell you. But those are the missions: to be a user facility, to do our own research, to create better magnets and better probes, and education and outreach. So that's been a lot of fun. And so what I want to just let you know, for the people that don't know about it, that's your refrigerator magnet. Okay? That's about 20 times the Earth's magnetic field. If you want to get to really big fields, you have to do what I mentioned before is wrapping around. You have to use an electromagnet. And we make magnets that are thousands of times the Earth's magnetic field, millions of times the Earth's magnetic field. And so we'll show you why some of that's important. So just to tell you, so there's 3 campuses: Florida State University in Tallahassee, Florida, Gainesville, University of Florida, and Los Alamos. At Florida State University, we have 4 user facilities. And I won't go into all details. I will give you some examples. But that's where we have our 45 Tesla continuous magnet. It's really, people want to use it all the time. It's easy to get in, so we're oversubscribed, but we'll help you write proposals, and we like first-time users. 45 Tesla. We also have 900 megahertz, means we do NMR and MRI at 21 Tesla. I'll give you an example for that. Then at University of Florida, we have 2 user facilities. One of them is high B over T. It doesn't go to as high field, but it goes to low temperature. So you can go to 17 Tesla at 0.5 milli-K. And then you can do MRI up to 21.7 Tesla. And then at Los Alamos, we have our pulse field facility. And if you look down at the lower left there, you see a normal-sized man. That is a giant, giant generator for getting the pulses. And those give you 101 Tesla, which is several million times the Earth's magnetic field. And so this is our Delta air map. This shows that, in fact, Gainesville, Tallahassee, and Los Alamos are hubs of Delta Airlines. Just kidding. And so this just shows you that we have a lot of users. We had 1,600 users from almost 160 institutions in the United States, and then from all over the world. We train hundreds of postdocs, new PIs, and we even, some of those places actually have their own magnet labs, but they don't have what we have. So they come to use our probes and our magnets from all over the world. And in fact, newcomers are welcome. About 25% of principal investigators are first-time users. You go on the website, maglab.com or Magnet Laboratory, you'll find it, and it tells you how to write a proposal. And if you've never done this before, that even gives you a higher chance of getting accepted. There are no user fees. You just have to get there, and you can stay with me. I've got a nice house. So then here are some of the latest and greatest hits. But what I want to show you is this is that in 2021, the NSF gave us money for a 40 Tesla magnet. It'll take about 10 more years just for the design and testing. It's a fantastic project. Now, we already have a 32 Tesla magnet, which won in the United States the R&D 100 awards. The 32 Tesla magnet is an all superconducting magnet. Those other magnets have copper in them, and they have to cool them with 550 psi of water, and they're noisy. With an all superconducting magnet, you can do a lot more quiet measurements, and there's other things that you can do with a superconducting magnet because things are already cold that you can't do with a resistive magnet. So this is the strongest superconducting magnet in the world. And not only is it the strongest superconducting magnet, but it's a user facility. So when you read about people making magnets for fusion and they made this magnet, et cetera, they get one shot and then they break. And one thing that we're known for at the Magnet Lab is to make magnets reliable and usable, and this has been in operation for at least a couple of years, and it's great, it's reliable. Now you may wonder, why do you go from a 32 Tesla to a 40 Tesla magnet, and why does they take 10 years in just the design phase? It's because every Tesla takes a lot of energy. And when you go from 32 Tesla to 40 Tesla, you have like, the 32 Tesla is about 20% of the stored energy of the 40 Tesla. So it gives you a lot more energy and can get you more to the basic physics that you want to learn. And I'll show you some of that now. So our science highlights are in three main areas: materials, energy, and life. And I'll start with some materials examples. So one materials example is a little bit specialized. Remember when I told you below a certain temperature, some materials are, most materials are actually superconducting. And when you raise the field, you stop the superconductivity. You break up those electrons that are working together. The magnetic energy says, get away. So what this is a plot of here is that we have at the bottom here, where it's blue, it's superconducting, and that x-axis is a function of angle. And as you raise the temperature, it's at low temperatures, you raise the field, these white areas show where it's not superconducting anymore because the high field broke the superconductivity. What's really strange is that green area in the right side. When you bring up the field above 30-some Tesla, the superconductivity turns back on. It was completely serendipitous. It started a whole new field of physics. Some of this work is done at the DC facilities in Tallahassee, some at the Pulse Field facility in Los Alamos. But there's a lot of people working on this now. And that weird superconductivity in the green area looks like it might be kind of where the electrons are lined up in another way, and can it be used for a qubit, for quantum computing? Probably not, but it works on proposals when you say that. This is my second example of materials, and we develop new superconductors that are useful for all kinds of things. Our biggest funder of superconducting materials is high energy physics. We developed a material at the Magnet Lab that they're winding at at Lawrence Berkeley Labs, and they're shipping to CERN. Well, and it's just a conventional superconductor. The reason is that we're able to make the material that it can withstand a magnetic field so much better. And that change is now being used for the high luminosity upgrade in the super collider at CERN. And it's going to give them 10 times more the brightness than they had before. Now I want to give some energy examples. The two people like these more. So even though I'm a materials physics person, these are really cool. So I want to give you the energy one they're both going to blow you away. Okay. So one energy example is we have something called ion cyclotron resonance. Okay. What does that mean? Ion cyclotron resonance, ICR, you can imagine what's going on. It's like a cyclotron. You put something in there. It was developed for oil. You put a spit of oil inside this big magnet, and you chirp it, and who cares what that means? But you can the heavier ones rotate more slowly, the lighter elements rotate faster. Mass spectrometry. This is a mass spectrometer on steroids. What's in the green there is what they call quantum time of flight, the primary competing technique, which doesn't have as high the resolution. What we have at the Magnet Lab is we can give you mass spectrometry to the resolution of about 1 electron. That's 1/2000th the mass of a proton. So that's very high resolution. And why do you want, by the way, that's what the spectrum looks like. And I don't know how to analyze them, but the guys at the ICR do. So here's 3 reasons why you want to do it. One of them is petroleomics. That's what it was developed before. If BP and Exxon drill wells, it cost them each $1 billion. If you sample the oil, we can tell them exactly if it came from the same reserve or not. We also do forensics. If there's an oil spill and they don't know where it came from, we can tell you decades later, we can tell you exactly which well it would have come from. Proteinomics. One of my favorite ones is protein folding, right? When a protein folds, its folding will determine what it does, okay? It's nature. So everybody's favorite protein, which I learned when I got to the magnet lab, is the P53. The P53 protein can be from healthy to malignant and everything in between, depending on how the folding determines its functionality, depending how it folds. By doing a hydrogen deuterium separation, we can tell you how the protein folds. Okay? And then finally, there's a whole lot of stuff in climate change and sustainability. So here's the climate change and sustainability. We sample, the permafrost all around the Arctic, so we can take a look at how climate change is progressing in different areas. One of my other favorite is that if you want to put, and they call it the build planet, you want to put asphalt down on the build planet, that water insoluble and water soluble, you actually want it insoluble. If you put the tar down and it's water soluble, it'll go into the aquifer. Bad for drinking water. So it turns out that the difference between those 2 kinds of carbon chains are very, very close. And if they're out, and we can tell if they're out of compliance or not. So that's another thing that it's used for. This is one of my favorite. This is actually fairly recent. So many of you know plastic bags bad. Okay. One of the reasons why plastic bags are bad, because they have these polyfluoro, I forget what they're called, but the PFAS, these long-chain fluorine molecules. The chemists are going to get mad at me in there. And they're carcinogenic and they're really bad for you. And they think they last forever. In fact, they don't. There was a series of experiments done at the magnet lab where they put tests and also bags from Kroger and CVS and Target, and they left them out in the sun, and they tested them again, and they found out that the PFAS actually do decompose. What does that mean for the environment? We don't know yet, but no one was able to tell that the PFAS decompose. Is it a good thing or a bad thing? Somehow I don't think it's a good thing. Okay, now we're going to go to some life examples. So most people in this room have been in an MRI, right? I've had several, The best, you don't have to raise your hand, I'm sorry, we have HIPAA rules. The best thing about being in an MRI is you get to go inside of a superconducting magnet, right? Very cool. And you wouldn't have that without superconductors, right? Typically, if you want to go above 1 Tesla continuous magnet, you have to have a superconductor, okay? And most of the time, when you go into a superconducting magnet in an MRI machine, it's about 3 Tesla, 2 to 4 Tesla, depending on the hospital, okay? Now, if you go at higher fields, you get higher resolution. Why? The way MRI works is you put something in a big magnetic field, and you line up the hydrogen. You're lining up the water. You're measuring the water. You're looking at the hydrogen or the protons, okay? And you line everything up, and you take a picture as if you change the field, things decay, and you can see where everything is. It's all an imaging technique. That's why it's so noisy, because they're always changing. It's the clicking of changing the currents in the coils, okay? And so you line things up, and then you take a picture with radio frequency light. That's how you get the spectrum. Now, it turns out that when you go into an MRI machine and they use a radio frequency spectrum, it's a very low energy radio frequency. But there's a resonance condition. The higher the magnetic field, the higher the frequency of the RF field. So if you're going to 21 Tesla, you're using a much higher energy RF field. Higher energy means smaller wavelength, means higher resolution. So this is a standard MRI where we can see it's about a 1 millimeter resolution. If we now do a 21 Tesla, we can go to micron resolution. So we do some of that. We don't want to do a long time because that RF frequency, it's not as bad as a microwave oven, but it's not that much fun. But you can see subcellular structures. So here's an example. This is actually fairly recent. It's an early test for Alzheimer's. Now, these are rats. It's not scaled up to humans yet. But what happens in onset of Parkinson's or Alzheimer's, you get these things called plaque amyloids that build up in the brain. And what happens when they build up in the brain, they make little microhemorrhages. Remember I told you that MRI typically measures hydrogen. So if there's little hemorrhages of water, i.e. blood, you can pick that up. And the hope is that if you start getting like loss of certain things, we'll have to scale this up to humans and have an early detection of Alzheimer's disease. This is everybody's favorite. This is an older piece of work, but this is not on hydrogen. Like I said, when you go into an MRI machine, they're looking at the water in your system. We're at such high fields. Let's look at something besides protons. We look at MRI and NMR across the entire periodic table. Here's an example of imaging sodium. Okay, sodium is a lot heavier than a proton, and so it turns out the RF frequency is lower. So it's lower frequency, so it's lower resolution. But you specifically pick out the sodium. Why do you want to do that? Well, it turns out that when cells are dying, they uptake sodium. We don't completely understand the mechanism, but that's okay. That's what happens. So the other thing I learned when I got to the magnet lab is you can go and buy a rat with a brain tumor. So here's an example on the left of MRI imaging of the rat's brain tumor looking at the sodium. You give the rat chemotherapy, you wait 4 days, you image again. And you repeat that until that tumor lights up. On the right side, it's brighter. Why is it lighting up? It's uptaking sodium. Since it's uptaking sodium, that's an argument that the cells are dying, and that gives you hope and confidence that that form of chemotherapy may be effective. And then here's another example, which is, this is very, very recent. I think it's just been published. But you can label stem cells and watch them with image them in real time, fMRI in the brain. So what this is an example of is giving someone stem cell therapy, again a rat, giving a rat stem cell therapy and imaging where the stem cells are going if they're affecting the stroke. So this is something else that's been very used. Okay, so that's the magnet lab. I have a few more minutes, right? Okay, I'll go on for 6 hours. I lock the doors. Okay, so back to this stuff. Take a break. I showed this to you before, okay? I said superconductivity was discovered in 1900. I know I should point to both screens. Sorry about that over there. I'll walk over here for a little bit. So, superconductivity was discovered in 1911, and every year TC gets higher, and everything in red here is what we understand, the conventional superconductors. Everything else, and I've left most of the families out. There's probably more than 50 families of these unconventional superconductors. So this plot is the temperature at which it superconducts over time, and that blue stuff, as you've heard of the high TC revolution, that's when high temperature superconductors were discovered. Those go up to about 150 degrees Kelvin, okay? It's amazing. And then there's all these other materials. They all have something in common. On that lower right, I have something called the phase diagram. And I'm going to expand that in the next picture. So what that is that we have on the y-axis is temperature. On the x-axis can be pressure or some other thermodynamic variable or doping. So if you take a material and you can put in, it's actually not that difficult. You can change the composition and put in more electrons or less electrons. And you go across that x-axis, what do we have here? So the y-axis is temperature, and across this x-axis is this pressure or doping. On the left side is typically a really lousy metal. It can't even be an insulator, but it's something that has pretty strong electron correlations, and I'll explain what I mean by that. Over on the right side, we have something called the Fermi liquid. It's like copper. We understand that completely. So we understand most of the things over here. Now the superconductor. Remember I told you that there was a BCS superconductor, and I told you that the electrons were correlated. The difference between what we understand in the conventional superconductor is why they're correlated. What we know in all the other superconductors, the hundreds and hundreds and the 50 families of other superconductors that we have, is that the electrons are still correlated the same way, but we don't know what's causing them to stick together. Okay? So we don't know what the mechanism of this BCS Cooper pairing is. But there's more in that. But we do know, but they are Cooper paired. So in fact, there are equations that can explain how a superconductor behaves. It's optical, magnetic, transport, and all these other properties. We can write down, and we understand how they behave. We don't know why they work, but we know that they work. They know they have certain optical, thermodynamic, and transport properties. That's also true on the right side, the simple Fermi liquid. We have electronic structure calculations that can tell you how silicon, how copper, how gold, how they conduct with their optical properties, et cetera, et cetera. What we don't have, what's unsolved, is this area up here that I labeled unsolved quantum matter. Remember when I told you things kind of line up and stick together in funny ways? That's what we don't understand. So moving right along here. This is an overview, okay? So of those 50 kinds of superconductors, they basically all, and it's quantum mechanics, so nothing is complete. Quantum mechanics means there's always something a little rubbed out, and when you say all, you can always find an exception. But almost all of the unconventional superconductors show this same phase diagram. So I didn't show you the other one, but here's where it was discovered. Actually, this phase diagram came from one of my friends that's in Cambridge, Gil Landros. So they found this weird material called a heavy fermion. It means if you measure the electronic mass, it's way too strong, too big. And it's because the electrons are kind of working together, okay? So what you find on the left side is typically an antiferromagnetic, terrible metal, sometimes an insulator. On the right side is a typical normal metal. When they meet at low temperature, you get this dome of superconductivity. We don't know why. But basically, all the superconductors, this is the high temperature Cooper rates. I didn't have data from my lab. I have it later on. But these are just all these other materials that at high temperature, okay, we don't understand what's causing the electrons to behave the way they do. We completely understand the right side, and we can model what's under the dome. Unsolved problems. Moving right along. So something about this dome. I like to bring this up. I didn't notice this, but we all kind of noticed it at the same time. You need to have this weird correlated behavior to get high temperature superconductivity. So on the left side, I said it's really, really a bad metal. Those are very, very strongly correlated, but not correlated like the superconductors. It's different ways. Like you can get these stripes, you can get insulators, things that look like on paper they should be a great conductor, but they insulate. It's because the electrons lock arms and say we're not moving. We don't understand it, okay? So we need this kind, all high temperature superconductors have this weird kind of correlated electron behavior. But if it gets too correlated, a dome means it's low on both sides, okay? So if it's too correlated, it drives TC down. If it becomes weakly correlated, like a Fermi liquid, it drives TC down. So too many correlations are bad. Not enough correlations are bad. You got to find something in the middle. So I guess it's the baby bear and the mama bear. I don't know. So basically, they all have this unexplained quantum material stuff. And that's pretty much what I studied most of my adult life. So these are just some, this is data from my lab, okay? So what we have here is in these, I'm just repeating myself now, across this phase diagram, you have superconductivity, you have this over here is going to be Fermi liquid, over here you're going to have some weird, typically antiferromagnetic behavior. And what we were able to measure a few years ago is we can directly measure this electron nematicity. So let me just show you. The TC on this material, where the electrons correlate to be a superconductor, is like 20 degrees Kelvin. These kind of electron correlations come at like 170 degrees Kelvin. Let me just tell you that one kind of electron correlation, okay? At these higher temperatures here, above this kind of chartreuse area, if you look down on the lattice, it looks square. It's a tetragonal lattice, which means looking down on it, it looks square. So typically, in a material, the electrons would say, okay, I have to be in some kind of square configuration. But in fact, at a very high temperature, these electrons kind of grow into like cigars or sausages, whatever your favorite thing is. And they're not doing what the lattice is telling them to do. And that's surprising, because the way we understand electronic structure is that, I'm going to repeat this later on, is that the location of the atoms in the lattice and what they're made of determines the electronic properties, but only for a Fermi liquid, not for these kinds of materials. So they're still unknown. So these are just examples that, these are a laundry list. I'll go on to the, this is, you don't expect to learn it. There's a laundry list of some of the properties. And this is a laundry list of, just to let you know, I'm going to test you on this. Okay, no. Just to let you know that what's happened over the past 30 years or so is we have more and more techniques of measuring these quantum materials. And if I have time, I'll flash you one slide of an experiment, a recent experiment. The only way that was possible because the crystal growers have gotten so much better at growing the crystals. They're such a high quality. And third is computation. So we have our new ways to look at these dozens and dozens of quantum materials through new kinds of measurement, growth, and computation. So that's going to lead us to this. Okay, what is unsolved quantum matter? So the unsolved quantum matter is what I told you, like this nematicity and these stripes. The solved quantum matter is this superconductors and Fermi liquids. Okay? So my general example is that, remember I told you that you can calculate the properties of copper? You can't calculate the electronic properties of this unsolved quantum matter. And remember I told you that one of the reasons you can't is because the electron-lattice interaction is not as strong as the electron-electron interaction. That's not understood. Why the electron-electron interaction is so strong. Why these electrons at high temperature says, we know you're a square lattice, we're going to turn into little sausages. Okay? So that's one of the things that happened. So let's just remind you, this is the free electron theory of solids. Okay, this is what Mr. Fermi figured out a long time ago, and other people, Landau. So what you have at conventional superconductors above TC, above their superconducting transition temperature, they don't have that crazy phase diagram. Above the superconducting transition temperature, it looks like copper. It looks like a conventional metal. And then when you lower the temperature, it goes superconducting. Those are understood. So the free electron theory of metals is that you have a bucket, and you start throwing electrons in, and they can't all go to the bottom because there's something called, Mr. Pauli told us about the exclusion principle, and they fill up, and that's the free electron, and we can calculate all these properties. And Bardeen, Cooper, and Schrieffer said, everyone says, it's not working in superconductors. And they made that explanation, which is how the electrons interact with each other through the lattice. Now we're going to talk about, so these are solved problems. Now in unconventional superconductors, they pretty much have all this phase diagram. So we understood what's going on the far right yellow of this phase diagram. That's a conventional Fermi liquid. We know how to calculate that. The blue part below TC, even if we don't exactly understand why it's superconducting, the superconductors pretty much have the same properties. They all have the same kinds of correlations, even we don't know what's correlating them. So those two are pretty much understood. But what we don't understand are the rest of the phase diagram, when you get these weird correlated electron phases. And that leads me to the analogy. Good, I have a couple minutes. Okay, so this is fun. So so a few years ago, I guess it was, 2016, so it was a long time ago now, I was on the Kavli selection committee, and I wasn't on this one. I was on the nanoscience one. But I went to all the talks, and it was fantastic. And Kip Thorne, before I won the Nobel Prize, gave this talk, and I looked at that picture. I took a picture of it, and I said, "Can I use your picture in a talk?" And he said, "Yes." And what I said was, that distortion, could that be an analogy with BCS? And I mentioned that all my friends decided I was certifiably insane. So I left. So I finished the lectures, went to the banquet, flew back to the Applied Superconductivity Conference in Denver, and by the time I got there, 56 hours later, I had the analogy. So I've tuned it a little bit. But they won the Nobel Prize in Physics for gravity waves, and it was an amazing discovery. So moving right along now, I said, can we correlate these? I'm sorry, correlation on the brain. Can we make an analogy? So this is basically the analogy. So we look at, so we look at what the gravity waves discovered, right? So we look at the detector LIGO. This is the most amazing telescope in the universe, right? $1 billion, the best $1 billion National Science Foundation ever spent. Why is this so cool? I told you the amount of energy. You know, this thing is these, kilometer-long tubes, and they measure the deflection of a mirror less than the size of a proton. It's an amazing detector. Why is it so important? Well, I'll tell you why it's so important. There's a couple reasons. I think the most important reason, we knew that was going to be right. We knew that there isn't a bunch of stuff out there that said there were gravity waves, okay? But for the first time, we have a way to look at the universe with a whole new telescope. It's not light and it's not matter. It's gravity waves, okay? We don't know what we're going to learn of it, but remember, the energy was more than the combined power of light in the entire universe. That's pretty cool. So we don't have one LIGO. We have 3 sets of families of quantum detectors and quantum materials with our dozens of unknown questions: growth, measurement, and computation. I only got a couple slides left. Hang on. Okay. So I like this one. So this was Mr. Newton down the street here. Decided that he pretty much solved it, right? He knew that what happens with gravity is that masses are attracted, and he wrote down m1 times m2 over r squared. So it's how heavy the mass, how strong the masses are, how massive things are, and their distance, 1 over r squared. Mr. Einstein said, doesn't work everywhere. And he looked at places that didn't work. Maybe you know of the retrogression of the perihelion of Mercury. It didn't quite work. Places were broke down. Plus the fact Newton's law is immediate action at a distance, which is also impossible, right? So that's when Mr. Einstein came up with this general theory of relativity. So the microscopic explanation of gravity is, in fact, a distortion in the space-time continuum. That's what those little dips are in the background, okay? This is my question, and this is like got from Kip Thorne's talk also, which was, will this new detector of the universe help us understand 2 of the greatest mysteries in physics today? What the heck is dark matter? What the heck is dark energy? We don't know if it'll answer it, but we have a new telescope. That's the hope. And we have the same question here. Mr. Fermi figured out that free electron theory of metals. Bardeen, Cooper, and Schaffer said, this is how it's going to work for a superconductor. Now we have dozens of quantum materials, but will all these different kinds of detectors help us understand the dozens of kinds of quantum materials? Now to push the analogy one step forward, I promise this is my second last slide, I think. Probably, yeah. So, so to push this one step forward is that, to remind you, gravity, Newtonian classical theory, is determined by the forces between objects and from the masses in them, right? So m1, m2 over r squared. We have the same thing in simple metals. The properties are derived from where the atoms are, right? Where the atoms are and what the atoms are made out of. So that seems pretty good. And then we go on to the Einstein general theory. The masses create distortion in the space-time continuum. That is the microscopic theory of gravity. And we see that the electrons create a distortion in the lattice continuum. That's the theory of BCS theory. And again, will LIGO help us understand dark energy and dark matter? And will electron matter, these correlated electron materials, we're still, when they tell you someone solved something, they haven't. I've been in this field a long time. There's a lot of questions to solve, and I keep feeling like I'm around the corner, like fusion. Okay, this is my one graph. Okay, this is fairly recent work, not that recent anymore, but what it shows is that we think that the pairing in this particular heavy fermion material is due to, see, it's called cerium, cobalt, did I even write that? Yeah, cerium, cobalt, indium 5, and it's got cerium in it. And what happens, the electron goes to the lattice and it feels the cerium, which is called an F level, and it picks up. And so these data are supportive that we think we know, we're not convinced everybody yet, why the electrons are correlated, and has to do with that cerium F level in there. And I'd be happy to discuss that, but not in this audience. Okay, here we go. So superconductors need to be cooled, and they're really cool. There's many families of, I didn't put right in there, come to the magnet lab. Okay, many new exciting ways to measure, grow, and compute, and we think that the answers are right around the corner. And so this is still exciting times, and I thank you for your time. So for the questions, I'll hide behind here. Okay.
Thank you. We are pretty much out of time. I would say physicists who are specialists in Laura's field, questions afterwards. So general questions from non-physicists.
Particularly students.
Particularly students.
What's your favorite
anything.
color?
Can you catch?
Hi, is it on?
Should be on.
Hello? Hello? Is it on? Hi, thank you for your talk. It was really insightful. Can I just ask what dark energy is for dummies?
Well, I'm not an expert, but it turns out nobody is. So what was determined, so if you have something like, so if you drop a ball and it bounces, it doesn't come up as high, right? And unless you have flubber, right? So it bounces, doesn't come up as high. Dark energy, if you drop a ball, it'll go up much higher. The way it was discovered was looking at the center of the galaxy. As things went around the center, they found they accelerated. And there was no known explanation. And the only explanation that Saul Perlmutter and other people came up with, which got them the Nobel Prize, I can't remember what year, was that there's this energy that's accelerating things. So we don't really know what that means, except that, before this was discovered, we thought the universe was slowly expanding. Now we know it's accelerating and it's expanding. So we're going to cool off faster than we thought. We'll freeze to death within, I don't know how many millennia, but so. That's good.
I'm chemist, not physicist. I'm quite wondering about, so chemistry, we engineering molecule. Physics, you engineering nuclear, engineering electron. I imagine is any final structure with the electron.
Any what structure with the electron?
Even smaller unit within the electron. So electron looks.
Oh, so again, this isn't my field, but certainly within protons, there's quarks, and it's really complicated. From what I understand in high energy physics, the electron doesn't have a structure. It's really considered a point particle. It's for me. Oh, sorry. But it does have interesting properties, right? It has charge, and it has spin, and its charge and its spin are both quantized. So that's pretty cool.
There are physicists who measure the dipole moment of the electron, and so far that's been shown to be zero. So experimentally, as far as we know, it's a point particle.
One question is, we have different elements, so hydrogen to like sodium. Would the electrons in hydrogen and in sodium the same?
Yeah, same electrons.
It's amazing.
It's amazing. Better living through chemistry. What can I say? It is really, I mean, that's why I like that first slide about dark energy of quantum materials. There is some kind of unification, which we don't understand. Now, I don't really believe there's a grand unified theory of everything. I don't believe that for a second. I do not believe there's a grand theory of superconductivity. But there are interesting things that they look alike. So.
Thank you. Yes, and you talked about the Magnet Lab doing work about sustainability and climate change and that sort of thing, but also talked about them working with the oil industry. And I wondered if there are ever sort of ethical concerns about working with two seemingly competing areas.
So we're a user facility. So I put on like these little walls in my head so I can work. And I worked in a laboratory Bell Corps where we had different people paying us to do research. And so we had to learn how to compartmentalize. So there is no problem. And in fact, with the oil industry, well, we're going to burn oil, right? Unfortunately, we're going to burn oil for a long time. But besides figuring out where the oil comes from, we also, as I mentioned, oil is the most complex fluid on the planet. And to take it from petroleum to something that's going to run your car is a multi-step process. And our analysis of the oil can have it happen more efficiently by seeing exactly what sulfur is in there, et cetera, et cetera. So I don't consider them, I don't consider that an ethical problem at all. But then again, that's me. I am vice president of ethics with IUPATH. So.
Right. Thanks, Laura, again, and all those physicists. Please come to the front and have a chat with Laura. We have a little time before we'll disappear for dinner. Thank you very much.
Thank you.